Welcome viewers. Today we want to look at analysis of temperature load in bridges, and we are going to look at the code of practice, the British Standard BS 500 Part 2 1978, and as well as BS 500 Part 4 1978, Table 3. Okay, now let's start by looking at the analysis of temperature on the structure. We know that on a very hot day, we have the sun transmitting radiant energy on a concrete surface like we have on the board. When the sun transmits radiant energy from on the surface of the structure, what happens is that at the immediate surface in contact with the sun, in contact with the heat energy from the sun, the temperature of the structure rises. At this point, we're having a high temperature at the surface of the structure. Now, once the temperature rises, you will know that as you cut across a section of the structure, you discover that inside the cross section at certain depth of the structure, the temperature at the surface is quite higher, comparable to that at a certain depth along the cross section of the structure. Okay. Now, what happens eventually is that we're going to have a difference in temperature as well. It will result to difference in the stress across the section. Okay. Now we look at what happened in this place. We discover that when the heat energy from the sun is transmitted into the concrete structure, what happens? We're going to have some level of expansion, and the expansion is not going to be uniform like you've seen. I've drawn it on the board. You can see that we're having some kind of curvature at the very top of the structure. You can see that there's a little bit of expansion which varies along the cross section because of the differences in temperature. Now we have a non-uniform stress that will be induced on this structure. So we have expansion uh, due to positive temperature change, and that will induce stress across the cross section. Now we can also have a situation whereby on a very cold day, when the temperature of the atmosphere is very low, we are going to have we'll have temperature as low as minus degrees Celsius. You are going to have a reversal temperature, unlike where we have high temperature at the surface. In that case, where temperature becomes very low, as much as a minus value, you are going to have contraction of the structure. So once the structure contracts, you see that there's a reduction in the size, and it's not still going to be uniform. Okay, so what we are going to be seeing is contraction and reduction of this structure due to temperature variation. So we have temperature variation which cuts across the section. All right, now we come to thermal expansion. We know that the coefficient of thermal expansion, alpha, we have it as a change in length over the original length divided times theta. Okay, where theta becomes our temperature difference. Okay, or temperature rise. Okay, now we have this change in length to become a delta L over L1 L theta. Okay, we can as well call theta our T, which represent our temperature rise. Okay, now we said that the coefficient of frictional for we said that the coefficient of thermal expansion for concrete, if we know that, we say let it be 12 times 10 to the power minus 6 degrees Celsius. We know that from Hooke's law of elasticity, we know that change in length of our original length is equal to our strain. So we have strain, which epsilon represent epsilon, which is epsilon here from Hooke's law. And we equally know that our modulus of elasticity, E, let's consider concrete in this case. So we'll say modulus of elasticity, E for concrete, is the stress ratio of the stress in the concrete to the strain. Okay. Now we know from that stress is force over area, while strain is change in length over original length. So we can as well say that if we are talking about a coefficient of thermal expansion of this structure, it means that we are going to be having, why this entity represent represent our stress. We are going to be having our strain, our coefficient of thermal expansion, which represent our strain over our theta. So that's why we have it here. So strain becomes alpha theta. So we can therefore say that modulus of elasticity becomes alpha stress, while this one represents our strain. So this is within our stress, which is this whole entity, is equal to this times this. But for a 1 degree rise in temperature, we'll say for a 1 degree rise in temperature, we can say that stress becomes as modulus of elasticity times a coefficient of thermal expansion times that 1 degree rise in temperature, and that will give you EC times alpha. Okay. So now we want to look at our code. Now the code of practice has given us different groups of structures from group 1 to 4, different groups of structures numbered 1 to 4. There are various loads in terms of temperature variation. We'll look at the extreme case for positive temperature and the extreme cases of reversed and negative temperature. So we're going to look at the code and we'll look at some of these groups from 1 to 4, the different kind of structure. We have I section, we have concrete slab bridges, we have bus girder bridges. All of them have different load temperature range. Okay, so let's look at them from our code. All right, so we're going to look at the various groups of structures. We have this one, we have the bus girder bridge, comprises of steel deck and concrete section. This under group 1 is group 1, so you can see group 1. The surface here is 40 mm surface. Now you can look at the temperature variation. We have T1, T2, T3, T4, and you can see the values is T1, is T2, this T3, this T4, 24, 14, 18, 8, sorry, 4 cm. H here 0.1 meter, 0.2 meter, 0.3 meter. Now you can as well see the reverse temperature on this other side. You can see the reverse temperature. The reverse temperature is a negative temperature. You can see we have T1 here. So you can see that the value for temperature at the top is much compared to every other part of the structure. Now our H, which represent the overall thickness of our H here represent the overall thickness of the structure. Okay, now this is for group 1. Let's say group 2 structure. Group 2 structure will have the group, this group 1, this is group 1, this is group 2, steel deck on steel truss or plate. Use difference as concrete deck on steel box truss or plate girders. Now you can see it here. You can see group 3 here. So this is group 3. So we're talking about concrete deck on steel box truss or plate girders. Okay. Surface of the finishing is 100 mm for the surface. Now let's look at the temperature on this side. You can see the temperature T1, the positive temperature. We'll have it here. While here we have 4. We can look at the depth of the section. We have, in this case, we are dealing with the concrete. We're dealing with the concrete at this point. So we're talking about this concrete. So H here becomes the thickness of the concrete slab. Okay. The reverse temperature we have here to be 8, H2, H1, and the whole of this place represent H. Okay. Now, if you look at the table, you can as well see the values here, H in meters and T1 in degrees Celsius. Okay. So that is that for that. Now, looking at group 4, we are going to have concrete slab or concrete deck on concrete beams or concrete bus girder. So you can see, for example, concrete bridge slab, the thickness here is H. Surface remain 100 mm surface. This surface could be asphalt. Now you have a bus. You can see that 100 mm the surface. This is the thickness. This is for bus girder. We can look at their temperature variation here. You can see the temperature variation for positive and negative temperature. Now this one is for positive temperature. You can see when H is less than 0.2 meters, look at H here. For example, this composite section, when H is less than 0.2 meters, you have the temperature to be 8.5. Okay, greater than 0.8. H is greater than 0.8. You can see the temperature, the maximum temperature T1 here is 13.5. T2 is 3. T3 is 2.5. The reversal temperature is also here. You can see when H is less than 0.2 is here. When H is greater than 1.5, you can see the temperature T1 8.4, T2 0.5, T3 1.0, and T4 6.5. Now let's look at the temperature diagram. For the reversal temperature side, you see that on this side we have our T1, T2, T3, and T4. You can see their various height. We have H1, H2, H3, and H4. All right, so let's consider example one, like we've seen in the BS 500 code. I would like to look at this illustrative example. We have a composite section comprises of an I-beam, and we have a top slab of 225 millimeter. Now we have the centroid of this composite section E1 to be 0.692 meters. So from the surface of the beam down to the neutral axis, the overall depth of the section we've seen is 1.445 millimeter. All right. We just bring out from the code, we have T1, T2, T3. We have H1, H2, H3. Okay. So now what we are going to do, remember that from the code that we just looked at, we observe that this section belongs to group 4. And for group 4, we have the overall H for this particular section to be 1445 millimeter. Now for that same group 4, we have our H greater than 0.8 meter. So this H is greater than 0.8 meter. And according to our code, when that happens, our T1 is 13.5 degrees Celsius, our T2 is 3.0 degrees Celsius, our T3 is 2.5 degrees Celsius. Okay, so we have that already slated in the code. Now we have H1. We know that H1 is 0.3 H, so H2 is 0.3 H, and for H1 it must be less than 0.15 meters. Okay, so H2 also must be greater than 0.1 meters. So we must ensure that these two set the upper and lower limit of the upper limit of H1, while 0.1 is the lower limit of H2. So we can work that out, and we know that our H3, according to the positive temperature diagram, we know that H3 is equals to 0.3 H, and we are told that that H3 must be less or equal to 0.1 meter plus surfacing. All right, so in this case, we discover that our H3 is 0.3 H and is lesser than 0.1 meter plus our surfacing depth. Our surfacing depth, like in this case, we are assuming that we have asphalt on top of the deck slab, and that asphalt is about 100 mm thick. So if we have that, we can therefore say that our H1 is 0. We can start with that. So if we work that out, 0.1 meter plus an asphalt thickness of 100 mm, so we have a 0.2 meters. Okay, so we are saying that H3 must be lesser or equal to 0.2 meters. So take note of that. Now let's choose the value for H1. Starting from H1, we've worked out H1. We see that 0.3, like we have it here, 0.3 H is equivalent to 0.4335 meters. Okay, and that value, like we see, is already greater than the limit set by the code, which says the limit should be 0.15 meters. So since it is greater than the limit set by the code, all we need to do is to choose the highest, the upper limit, which is 0.15 meters. So I say choose H1 to be 0.15 5 meters. Okay, now let's go for H2. We are told that H2 must be greater than or equal to 0.1. So let's check and see our H2 here. Our H2 is greater, so it is okay. So we can say our H2 is 0.4335 meters. So that one is okay. We can leave it. So it's adequate enough. Now let's look at H3. H3 is 0.3H. We know what 0.3H is. So if we work that out, it remains the same value, 0.4335. If we look at the limit set by the code, here we have it to be 0.2. So it must not exceed 0.2. So it has already exceeded 0.2. So what I'm saying here is that H3 should remain at 0.2 meters. Okay. So now we have gotten the value for H1, H2, and H3. Now the next thing we are going to do, we are going to calculate the moment due to this temperature variation. Okay, now let's go back and do that. All right, so having looked at the values we obtained from the code, we are going to carry out the design considering the temperature rises from the data we taken from the code, 13.5 degrees Celsius, 3 degrees Celsius, and 2.5 degrees Celsius. We lay out the pressure variation, the temperature variation according to the distance of the code. You can see from the top of the deck to a distance of about 0.15 according to the code. That is where we have a temperature of 3 degrees Celsius. At the very extreme fiber of the composite section, we have it to be 13.5 degrees Celsius. Now, from what we got, we know that our H2 was 0.4335 meters. We've solved for that before now. So we equally know that from the surface of the beam to a distance of 0.2 represent the bottom fiber will have 2.5 degrees Celsius. So don't mind this drawing. This is supposed to be somewhere around here. Remember that here we have here to be 231 mm. So this value is going to fall around this zone. Okay. So now let's look at some of the information we've gotten from the code. The modulus of elasticity of concrete, we've gotten it from our code, 31 kilonewton per 31 kilonewton per millimeter square. Okay. Now the concrete area, which is the area of this composite section, is gotten to be 0.9414 millimeter square. Okay. Now the centroidal distance from the bottom surface to the neutral axis, let's call it E1. So if the centroidal distance from the bottom surface to the neutral axis is E1, call it A1 prime. We have that section, that value to be 0.963 meters. Now the centroidal distance from the neutral axis to the top of the composite section is 0.482 meters. Okay. Now we have the moment of inertia of the section to be 0.2301 meter raised to power 4, and we have the coefficient of thermal expansion for concrete. You can as well get this one from the code to be 12 times 10 raised to power minus 6 rise in temperature. Okay, so having gotten all these values, the next thing we are going to do is to determine the stress for every degree rise in temperature. All right, so we have the modulus of elasticity of concrete times the thermal coefficient of concrete times per 1 degree rise in temperature. So we can have that and solve that. If we work that out in Newton per millimeter, square, you see that that stress becomes 0.372 Newton per millimeter square. Okay. Now this stress is stress per unit rise in temperature. So for every rise in temperature, the stress value changes. So for a 13.5 degree rise in temperature, we are going to have the stress value to be 5.022 Newton per millimeter square. For a 3 degree rise in temperature, we'll have it to be 1.116 Newton per millimeter square. For a 2.5 degree rise in temperature, we have it to be 0.9229 Newton per millimeter square. So these are the temperature variation and the equivalent stress variation for these corresponding temperatures. Okay, now let's take a look at the stress. If we redraw this section, we can fix the stresses on the cross section. We have it here, like we have seen in the board. Already know the area the stress are acting, like we have here. This is 0.15, so the whole of here then from 0.15 we have. All right, similarly, according to the code, we have the stress from the bottom fiber down to somewhere around here is 0.2 according to the code, and we've already fixed that. So the area that this stress is going to act is going to be the whole of this area. Why this one will act here? Why this whole stress, the triangular stress, will act on this point? Now take note, the stress in each of them, like the triangular part, is going to be an area load. Okay. Now let's look at the the values for this load, and let's work it out. So let's look at at this point, like we've seen. Okay, now let's look at it from this angle. We have, let's label this stress diagram 1, 2, 3. Okay. Now for stress diagram 1, which is going to affect a distance of 0.15 meters as stipulated by the code. Remember that the overall weight of this concrete deck span is 1.740 meters. Okay, so now the whole of this area will be multiplied by this stress. Okay, so we'll do that. Similarly, we will have from here down to here. Remember that the overall weight of this deck is 225. So once we have taken away 0.15 meters, we'll be left with 0.07 meters, okay, which is this portion that I've shaded dot dot. Now, what is remaining from the stress here is 1.116. So that stress, which is stress 2, will act on the whole of this area. Okay. Now, the next we are going to have under it is stress 3, which is going to act on the I section. You can see I've drawn it on the board. The I section originally have from this point to this point to be 0.204. From here to here to be 0.023 meters. Okay, and the overall depth from here down to here, which I've just shaded. Remember, there's a chamfer for the I section, but we're going to assume that the I section is the stress is acting on a surface that is rectangular in shape. Okay, so that's why I dotted this. I dotted this side. So the whole of this stress from here down to here is going to act on the whole of this rectangle. Okay. Now remember, the beam has at the top here of the beam we have a 0.46. So from here down to here, the total value is 227 millimeter. Okay. So that is, so the pressure from number three pressure, we're going to have part of it acting from here down to here. So that's exactly what I've done. So if you use similar triangle, you will find that for stress 3 that I've done, you will find out by similar triangle that this portion is 0.3385 Newton per millimeter square. Why this portion, which is here, remains 0.9229 Newton per millimeter square. Okay, so that is what we have for that particular section. Okay, so having done this, the next we are going to do is to multiply this stress by the area. Now let's start with the portion 1, which is the whole of this, that is covering the whole of this shaded part. For that portion, we are going to have that portion 1 will divide the stress into 2. Here becomes a triangle and a rectangle. Okay, so it means that the pressure here, if we minus 5.02 minus 1.1116, we'll have a 3.906 as the pressure for the triangular part of that load. Okay, so that remains 3.906 for the triangular part of the load. Now that triangular part, we are going to multiply it by the whole of this area. Likewise, we'll multiply the rectangular part by the whole of this area. Okay, now let's start. We'll call the whole of that point, which is the whole of this point, 1. For 1, axial force due to 1 above. Of course, remember these values are Newton per millimeter square. So I convert it to kilonewton per meter. So if we do that, we multiply by 1,000. So I'm going to have this, the area of this small part, which is 3.09, which is a triangular, a triangular area load. So I'm going to say half times, which is the area of a triangle, half times 3.906 times 0.5, which is the area of this point, 0.15 times 1.75, which is this one. So plus this small portion, we're going to pick it. Remember, the small portion now is 1.116. So we do that, we multiply it by the same area, we'll have the total force acting on that place to be 801.099. All right. Okay, so this is what we have for this portion. Now let's look at the second one, which we are called portion 2, which is going to be acting on this place, and that dimension is 0.075 versus 1.74. We do the same way. Now let me pick it, the stress, multiplying the stress by a value of 1,000. So we have this, then times the area, because we are going to also divide this into two portions. One would be a rectangular portion, and while one will be a triangular portion. So if we do that, that is exactly what we are saying. So we say for portion 2, we are going to have this 1,000 times 0.922 times 0.07 times 1.74 plus the area of the small triangle there, which we got by minus 1.11 minus what we got here. And what we got here, we got it to be 0.922. So if we work that out, we are going to have it times 0.07 times 1.74 times 1,000. So if we do that, we are going to have 133.038 kilonewton as the axial load due to that stress. Now, the last way, the third we are going to look at is the axial force due to pressure 3, which is this. Now, we can see I've redrawn pressure 3 and the area it is acting upon. These are the area it is acting upon. So, if we work that out, we'll break it into two. We have 1, 2, 3 portion. Now, for this is a rectangle, so it's going to multiply the whole of this, which is 0.460. The whole of this length is 0.227. So we do that. We'll say 1,000, 0.338 times 0.227 times 0.46 plus the triangular part, which is half 0.922 minus 0.338, the stresses, times this same area, this same portion, which comprises of 0.46 by 0.227. So that's exactly what I did, times 1,000. Then the last part we are going to have is part 3. This portion is going to affect this whole area, which is portion 3 is going to affect this whole area, and the width of the web of the beam is 250. So, and from our code, the pressure is going to act from here to here. What is left for this part is going to be from here to here, which is 1.5 mm. Okay, so if we work that out amicably, we are going to have 71.421 kilonewton. So now we've gotten the axial load for the stress, this particular stress diagram. Now the bottom of our beam, which is the bottom fiber, we also have a stress of 0.922. Remember, we have that temperature to be 2.5 degrees Celsius. Now, the code told us that that temperature must act over a distance of 0.2 meter away from the surface of the beam, which is from here down to here. So that is exactly what we have done. All right, so according to the code, we're going to have the bottom pressure to act from a distance of 0.2 meter away from the surface of the beam, so which is from here down to here. So you can see from my arrow here is 0.2 meters, and we know that the beam itself from here down to here in the beam, we have it to be 0.231. So the pressure is going to be acting on this shaded part. Okay, so we can say that the axial force due to this portion, which I call portion 4, is the area of this triangle multiplied by the area. We're going to have it as half times 0.992 times 1,000, which represents value for converting it to kilonewton per meter, times 0.71, which is the weight of the beam, times our value 0.2. We are going to have 65 kilonewton as the axial load. Now we are going to take the total axial load, for this, and this. So by the time we total it, we are going to have the axial load to be 1070.9 kilonewton. Okay, so this is the axial load that is acting on this composite beam. All right. So the next we are going to do is to determine the moment of the beam. What amount of moment, the restraint moment, is what we are going to look for. That moment that is going to cause the beam to bend as a result of these temperature changes. Okay, so we are going to work that out now. All right, so haven't gotten the stress diagram. Now we are going to look at the forces that are acting, because we intend to obtain the axial force that is acting on this beam. Now I've been able to draw the stress diagram. We can see from the board, we know the neutral axis is this zone, and from the soffit to the neutral axis we have 0.963 meters, while from the neutral axis to the top of the beam we have 0.482 meters. Okay, now we need to obtain the axial force and as well as the moment arm of the force, because we are going to take a moment about the centroid of the beam. This is the centroid. So starting with the first force, I call it F1. We've been able to discretize these two into rectangular and triangular forces. So here we have the F1 prime. I call this one F1 prime. This one is F1. Now the other portion which has been discretized also into F2 prime and F2, and their centroidal distance are also taken using the same subscript. Okay, now we have the centroidal distance of F1. I call it F1 prime. I call it X1 prime. That of F2, F1. Sorry, that of F1 prime, we'll call it X1 prime. That of F1, we'll call it uh, X1, okay, which is this. All right. That of F2, we'll call it X2. That of F2 prime, we'll call it S2 prime. So I will just take a moment about the centroid of this section. Okay. So having gotten this, we first of all try to obtain the forces. Remember, we've calculated the forces earlier on. So what we just need to do is to calculate the various forces. I call it F1. This one is a triangular load, so you know what to do to calculate this. Just go ahead. This one is a rectangular load, which I call our F1. All right. F2 prime is a triangular load. F2 is a rectangular load. So if we come this way, I have to shift the pressure that continues this particular portion, which is this portion. I have to move it this way for convenience, so that we can understand it clearer. So this one has been moved to this side. So if you come here, you look at it, you see F3 prime. The value to obtain it is also on the board here. We have the F3 prime prime, which is the first use of this rectangle. Remember, we've assumed the whole of this entity to be a rectangular section. All right, so we have F3 prime. If you do it, you are going to discover that the distance from here to here, the neutral axis, is 0.03. Okay, now we have what I call S. We have what we call F3 4, which means this part. You can see that there's an extension of the load beyond the neutral axis. So this one is going to act in a different direction to the others. Okay, so we have here to the 0.1015, 0.03, and you can see the measurement as it goes. So this, we are going to take this from here down to here, which represent this force. The value for the force here is 65 kilonewton per meter. Now, if we look at the values for F4 has been gotten. Like I said, that our F4, which is this particular force, is 65.5 kilonewton per meter. Okay, so similarly, we've done the rest and obtained the forces for each of them. For this particular portion, uh, this is not a square, but I'm going to assume it, like I said, assume F3 prime, which is this particular region. Assume that it's a square for easy calculation. So if we assume that we are going to have the force as 2.538 kilonewtons, okay? So having gotten all these values, the next thing we're going to do is to obtain the centroidal distance, because we're going to take moments of this force about the neutral axis, while all the force at the up about it. So they are going to be moving in opposite direction. So this one is moving in opposite direction. This one is moving in opposite direction to the neutral axis, while these ones are moving in opposite direction also. All right. So if you look at the board, you see that I've been able to derive the centroidal distance of each of these forces. Having gotten the centroidal distances, we cannot proceed to obtain the restraint moment due to temperature strain. Okay. Now you can see from the board, I've been able to multiply them by their centroidal distances. All right, so if you look from the board, you see that I've been able to multiply them by their centroidal distances. And if we do that carefully, you will discover that the moment obtained is 329.9 kilonewton meters, okay? Now, having obtained this moment, we are going to determine the stresses that are acting at the various fibers. We have three fibers. Bottom fiber, we have fiber at the top of the beam and the fiber at the top of the composite section. So now let's obtain the fibers. We already know the moment of inertia of the composite section. We know the sectional, can obtain the sectional modulus since we know the centroidal distances from the top to the bottom. We can as well obtain the axial stress, which is usually, in this case, is going to be a tensile stress because the beam is under tension. So we're going to have a negative stress due to tension as the axial stress. So we obtain that value. All right, so looking at the stress diagram, we have seen the stress diagram, fiber 1, fiber 2, fiber 3. Now, this is the axial stress. Of course, we know that the axial stress is a tensile stress. Uh, we have at the top, we're going to have, for the bending, we're going to have the top to be made up of uh, tensile stress, which is a negative stress, while at the bottom, we are expecting it to be compressive because we know that we are going to have a curvature of the beam in this shape. So more tension will be at the top side of the beam. Okay. Now the final pressure or the final stresses are drawn on the other side of the board. But let's look at how to obtain that. We know that the sectional modulus with respect to fiber 2, we know that the centroidal distance from fiber 2 to the centroid is 0.257. So if we divide that, we have this as sectional modulus. That of the bottom fiber, which is this fiber 1, we know that sectional modulus is this. That of the top fiber, which is fiber 3, we know that the sectional modulus is this. Also, we are going to determine the stresses. How do we arrive at these stresses? Now, the first thing we want to check out for the bending stress, which we know the bending moment is known, sectional modulus with respect to the fiber that we are considering, which is fiber 1 in this case. If we do that, we have a 1380.9. Axial stress is the axial force, which we've gotten earlier on, divided by the area of the cross section of the beam. Okay. Now, the total stress, the resultant stress, or you can call it residual stress, is the stress obtained having the take into cognizance the total stress as a result of temperature rise, and you minus this, and you add this, and you add the other one, meaning we are going to have the residual stress in bottom fiber number 1 as the total stress, which is stress due to temperature rise of 2.5 degrees Celsius, which is 0.93 Newton per millimeter square, which now has been converted to kilonewton per meter square. So if we work that out, we'll have, at this point, um, we'll have a negative stress for bending. Okay, so we have a negative stress for bending, and we have that is a negative stress for fiber number 1. Well, can we look at fiber 1? Okay, we're talking about fiber 1. At fiber 1, we have positive stress for bending, which is here. So you can see the value for that stress for bending. We have that stress for bending to be 1380. So that is the 1380. Now, for that of the axial stress, which is tensile, is negative. So that is why we have it here. So if we work out the residual stress, we're going to have this as our value. Now let's go to the fiber number 3. Fiber 3, similarly, we do the same. We have sectional modulus of respect to fiber 3, which is a top fiber, and we have the stress due to bending is known, is 691. Axial stress remain constant. Residual stress become the total stress as a result of 13.5 degree rise in temperature minus the tensile stress axial, which is constant, and plus stress due to bending, which is positive in this case because we are at the bottom of the beam. So the bottom of the beam is, since the beam is going to have a curvature, the bottom is going to be compressive while the top is going to be tensile. Okay, so we have the residual stress to be this. Now fiber 2, similarly, we do the same thing. We're going to have a bending stress is known. The residual stress become the stress due to temperature rise of 2.5 degrees Celsius, which is 0.99229. If we work that out, we're going to have the residual stress to be negative, which is minus 583.02 kilonewton per meter square. So that stress is the stress we have here, is the negative stress. All right, so this brings us to the end of this lecture. So when we can work that of the reverse temperature for this problem to obtain the residual stress. So these are the stresses at the beam. So once the stresses are known, if you are designing this beam as a pre-stressed concrete, you have to take cognizance of this stress. If you are designing it as a reinforced concrete, of course, you can still do check for stress, which depends on the type of concrete strength you are using, okay? And you must ensure that all stresses comply to the limits set up by the code, all right? All right, so this brings us to the end of this demonstration. If you find this lecture helpful, do well to hit the subscribe button and hit the like button. I'll see you in our next class. I remain Engineer Obaga. Have a wonderful day and stay blessed.